Unger here from the MacMillan Space Centre with another edition of Ask an Astronomer. I'm here in my office, thankfully, as opposed to our last episode where we had our blackout. We had to go down and use the museum, but we're here in our offices on the unceded territory of the Musqueam, Squamish, and the Tsleil-Waututh, joined as always by our astronomer, Marley. Hey, Marley, how's it going?
It's good. I'm glad to have power and to have all my slides today because that was terrible.
Yes, and this is going to be an exciting episode. There's actually lots that's been happening since our last episode. Of course, if you're here in YouTube and you've got a question to ask about any of the stuff that we're going to talk about, throw that into the chat. Or if you have any question under the universe, throw that in there as well, because we'll always have time at the end to answer all of your questions. But Marley, some big news coming up, and I have a place in my heart for the ice giants in our solar system. They're always kind of forgotten about out there, so far away. But we've got some news to start off with about the last planet in our solar system, Neptune.
We do, and I do have to apologize to my grandfather because the show is not going to be anything that I told you I might talk about when I spoke to you earlier this week. Instead, we're talking about Neptune because this very interesting paper came out very recently about that, talking about how Neptune is cooling in kind of a weird way. So for some contextual information, the seasons on Neptune last 40 years. So 1 year on Neptune is 165 Earth years. It's much, much further away from the sun. And so seasons are much, much longer. And so it's been summer in the southern hemisphere of Neptune since about 2005. And astronomers really wanted to see how the temperatures were changing during the summer southern solstice. So just like Earth, Neptune also gets a solstice, and they wanted to see how temperatures would start to change. As we know, the solstice on Earth, the summer solstice is the longest day of the year, not necessarily the hottest temperatures, but potential for them, lots more sunlight. And so on Neptune, how would things change? And so what the team did, it was an international team of astronomers. They looked at the thermal infrared images of Neptune for about 17 years and to put together trends. So about less than half of a season on Neptune. So very, very small time period in context of how long the season lasts. And so despite summer happening and despite it being in summer and it getting up to the longest day of the year on Neptune, most of the planet continued to cool over the past 20 years globally. It kept on cooling. And globally, it dropped 8 degrees Celsius between 2003 and 2018. And when looking at the South Pole, it started to warm dramatically during the last 2 years of observations. Observations ran from 2005 to 2020, and so, or just after 2020. And so the last 2 years, the temperatures rose 11 degrees Celsius between 2018 and 2020. And so because the data covers less than half of a season on Neptune, seeing these dramatic changes is pretty odd for them to see such extreme changes on the planet.
Interesting. So I'm curious, Marley, because these ice giants are far away. They're hard to get to. We've only sent one spacecraft there. So how are we getting this data? Are we using the Hubble Space Telescope? What type of tools are they using to get these temperature readings?
So all of the data collected is the data is from ground-based telescopes. So they can't use Hubble. Hubble does not have an infrared instrument on it with the ability to see Neptune, and it's actually not sensitive enough. So they use ground-based telescopes like the European Southern Observatory's Very Large Telescope to track the temperatures. And this slide is a slide from their paper that I'll explain in a second. And so they also use data from the Spitzer Space Telescope, which is an infrared, or Spitzer Space Telescope, which is an infrared, images from Gemini South in Chile, Subaru Telescope, Keck Telescope, and Gemini North, which are all in Hawaii. So they use a great deal of ground-based telescopes, but these types of observations are only possible with extremely sensitive infrared images. And you only get those from very large telescopes like the telescopes I mentioned, which have only been around for the past 20 or so years. So really, we couldn't have gotten this information before these telescopes were built.
It's really interesting. So Neptune is going through these dramatic, climate changes. So not only is Earth going through some climate change, but Neptune's going through some climate change as well. Is there any possible reasons for why this is happening?
They really don't know because we haven't been able to look at Neptune and kind of like repeat the trend, right? Or see if the trends repeats. Because, 1 year is 165 years. We only have a small window to really observe it. And it's hard to get like repetitive changes and observe those because it takes so long for Neptune to get back to the same spot. So it could be really anything from just like a normal global event, some sort of storm that happened, or even like something odd going on in its stratosphere. Like we really don't know what could have caused it.
Yeah, and over the years, through the Hubble space observations, we've seen those tiny little white clouds that have changed dramatically since I first started looking at pictures of the planet. Because Neptune's atmosphere does have some very turbulent winds, almost constant hurricanes, right?
It's a pretty intense planet to be on, like wind wise and weather and climate wise. But it's hard to. It's better to observe it and see that it's happening, but getting a reason as to why it's happening is where the challenge starts to become once you gather the data. It's really hard to say definitively why those storms are changing or what's causing the dramatic changes in temperature.
Okay, so we're not just gonna blame the god of the sea, Neptune, for being angry.
No, and I just wanted to explain this image before we go on because it really shows the data quite well. So the relative brightness is just observed changes in Neptune's infrared brightness, which basically you could not read relative brightness and just read change in temperature. It's a measurement of change in temperature. And then of course, year on the bottom tracks the temperatures. So these blue dots with the lines are Neptune's, like an observation of Neptune that was taken with a change in temperature. So you can see how even as the year's going on, which would be further into summer for Neptune, it gets cooler and cooler. And the images on the top are infrared images. So the brighter the image, the warmer it's interpreted as being warmer. And you'll see as the years go on, if I get my little laser pointer, buddy, yes. The planet like gets cooler, and then the South Pole though gets warmer and then gets very, very warm in 2020, very rapidly between 2018 and 2020. So it's very interesting. The data is very, very interesting to look at, though it does seem to be back on a warming trend maybe, which is odd because now it's like halfway through summer. So maybe it should be getting cooler. Like it's just weird. Basically, we can't compare it to Earth that well. It's very different.
Right. Well, we do have a question in about Neptune from Sarah Stevenson, middle schooler from Kelowna. So we've talked that Neptune is far, but how far, like if you were to describe how far Neptune is from Earth, could you give us some numbers or relative numbers?
Yeah, I can give you on average, it's 4.5 billion kilometers away, which is, if I convert that to a number that makes sense, not in Australian currency, my bad. It's about 30 times farther than Earth is from the sun. So it's very, very far. Yeah.
And to give some context too, the only spacecraft that we ever visited with it was Voyager, which I believe arrived in the late 80s and it launched in 77. So it was about 10 years, probably a little bit more than 10 years for it to get there.
Yeah, it takes a long time to get there as well. And of course you can't, and when it comes to space travel and traveling to planets, you can't just do a straight line either, right? Because the planets are all moving. And so it takes a lot longer than you'd think.
And so like the last spacecraft that we sent near, relatively near there was New Horizons, was the last spacecraft to kind of, like, I guess, get in that vicinity. And that took about 10 years as well. So that's kind of the time frame that we'd be looking at to send another spacecraft there, which we'll actually be talking about in a little bit. But speaking of the sun, we've got another big story about the biggest star that's relative to us doing some stuff up there. What's going on with the sun, Marley?
Yes. Oh, sorry. The paper that the Neptune stuff came from is open access, so you can go read it yourself. It's free. So if you have urges about it, but the sun is doing some solar flare stuff for the past couple of days. It's actually done 2 and one again last week on the 17th. But this one that you're seeing in the animation there with that bright flash on the lower right-hand corner, that's the solar flare. So this occurred at 11:57 p.m. Eastern time on Tuesday, which was April 19th, and it ended up causing a shortwave radio blackout over southeastern Asia and Australia. So people using ham radios may have noticed loss of radio contact. at specific frequencies for as much as an hour. So a solar flare is a burst of radiation coming from the release of energy associated with sunspots. So those black spots you can see on the sun. And we see them as photons or the light released. And the flares will release light at almost every wavelength on the electromagnetic spectrum. But we usually monitor the flares in X-ray and optical light. That's just what we look at them in. And this type of flare that happened, it was what we call an X-class flare, which is basically just the strongest type of solar flare there is. If you think about, I think it's like tornadoes and hurricanes, there'll be different like categories, like an F5, and then there's like G something, and then there's numbers beside them. It's a very similar thing with solar flare. So X is just the strongest type. The radio outburst it causes what we call a type 2 radio outburst. And what that means is that a type 2 radio outburst is caused by shock waves on the leading edge, so the edge coming towards you, of a coronal mass ejection. And a type 2 one just happens at a specific radio frequency. So in this case, a type 2 is anywhere between 20 to 400 megahertz is the frequency where that will impact. So the CME is not a solar flare. The CME is what we call a coronal mass ejection, which is a bunch of charged particles and plasma. So like parts of the sun, and which, they can come hit Earth and interact with our atmosphere and cause those really intense auroras. So aurora borealis, or why am I forgetting the one for the Southern Lights? But the Southern Lights. Thank you, aurora australis. And so there was a chance of auroras. People got kind of excited, like, oh, could we see some beautiful lights happening? But if you notice where the solar flare happened, and that's where the CME occurred, you'll see that it's on like the very edge of the sun. And so since the region where that occurred is on like the extreme edge of the sun, it's not likely that it's going to hit us. It will have moved a different direction, and we would have moved out of the way. So it probably won't have an Earth-directed component.
Okay, so then just looking at this, if you just back to that previous really cool image, this is an X-ray image of the sun, which is why it's got that really cool color to it, because it's not in visible light. But so that bottom right of the image, that's where the flare is coming from, and the rest of the sort of like bright areas are possible CMEs.
So yeah, this one is just showing the flare. The CME, I wanted to get an image of it, but the file size was too big because it goes through several days of the sun's activity. But it's on like SOHO. If you like SOHO NASA, there'll be a thing about it. That's their observatory. The ones on the upper left are actually other sunspots that are causing activity. So the sunspot that this solar flare originated from is sunspot 2992. In this lower corner here. And this, whoa, I want a pen. I want my laser pointer. There we go. And this was the sun on April 19th. This is where the solar sunspot was, just on the edge here. And then April 20th, it's gone. So it's now moved out of view. So we'll probably be fine. Whereas those other little swirly parts on the upper left were the sunspots from up on this corner here. And they have very fancy, like a active region 2993 dash something. But these sunspots are what are causing this area up here.
Very cool. And we do a lot of solar observing, usually in the summertime when we open up our observatory, and we do put our solar filter on. And in that image that you're showing right now, Marley, we do see those dark spots. It's really cool to compare to the Solar Dynamic Observatory images as well, so that you can see what we see in visible light and compare it to what the observatory sees in X-ray light. Very cool stuff. We've got some questions back from Sarah. So just to go back to Neptune for a second, Marley. Neptune, gas giant. Can we walk on it? Can we land a spacecraft on it?
So Neptune is categorized as like an icy giant. So it's gas and ice kind of combined. It's not really, doesn't have a true surface, you would say. So it's not like it's got a flat surface of ice underneath a bunch of clouds. It's like gas and icy material mixed together, all swirling around. So we can't really land on it at all, no.
But certainly its moon Triton, which has certainly been noted as being one of the really interesting places that we could visit, is a moon of Neptune that we can land on.
Yeah, we could land on that. One's like a rocky, icy moon as opposed to a gaseous. Most moons are rocky, icy, actually, now that I think about it. They don't really have gas moons.
And then back to the solar flares. So you had said that this solar flare was probably only going to impact Australia. Why is that?
It only impacted Australia just because, well, it happened like nighttime for us. So the sun wasn't even, like we weren't facing the sun. Our side wasn't facing the sun. And Australia just got like the full brunt of it because that was the side that was facing the sun. And so when the flare and when the CME came out, the energy just like hit the atmosphere in that spot, as opposed to, hitting globally the entire planet. So it was just in the way. Like that happens with CME. Like it was like the CMEs, especially like with that one being on the edge of the sun, there's no component of it that's going to hit Earth. Like it has to kind of line up the right way. Because keep in mind, it has to travel quite a long distance. And it's not just going in a straight line. That plasma is kind of like, it's like an explosion, right? So it's all going in different directions. And so only a part of it has the chance of hitting the planet. And so it's like a time and place sort of thing.
Yeah, and these must also be very concerning for the astronauts that are on the International Space Station, right? Because if either of these were to hit the space station, that would cause some big problems for them, wouldn't it?
Yeah, it probably causes a fair amount of problems. Yeah, it messes with frequencies, and the larger the CME, especially, it can mess with telecommunications and things like that, which would be a big problem because they'd just be up there with no way. But the good thing is that we're always watching the sun, like the Solar Dynamics Observatory, SOHO, we've always got eyes on the sun in some way or form. And so we can give an advance warning and like kind of have an idea that something's happening.
Awesome. Still sticking with solar flares from Harry. Is it possible for one that would be so powerful in extreme form to affect our computer systems, to really kind of like affect like our daily life? Is that possible?
Yeah, it is. There was actually a really huge solar storm, I think in 1887, and it actually caused like telegram machines and telegram wires to like spontaneously ignite, just because there was so much extra energy through the wires that they just like combusted. And so that it could mess with our systems. But you'd see it like mostly like GPS, anything that goes up and talks to a satellite could be impacted. Yeah. So your phone, like Google Maps, like probably not going to work. ATMs would start going down. So it is possible.
Yeah, and like our life is a lot different than it was back in the 1800s. So we are much more reliant on using electricity, and all of our systems are kind of tied to it. I can imagine that it would cause a lot more disruption to day-to-day life than it did back then.
Well, it's still like it's called the Carrington event, if you wanted to look it up. But it like people who worked in mines, like miners in Virginia, like woke up super early because the sky got so bright. Like like aurora just went got very active and very, very intense. And there were like aurora borealis as far south as Texas that could be seen. So it just was so much energy. The sky got very bright. And so miners like woke up early for their shift at the mine, but it was like 2 a.m. And wow. Very interesting. That was like in 1887. And then there was another one that missed us in 2017 that had the possibility of being like that level of intensity.
Interesting. Still sticking with solar flares and outbursts, and you had categorized them by saying like type M and different types. So what are how do we classify those different types? And sort of where does this more recent one align in that scale?
So the most recent one that I'm talking about was like an X type solar flare, and it just has to do with how energetic the particles coming off are, like the intensity that is headed towards us. So M is lower and X is the highest.
Is there a reason for those letter scales? They always seem to be so random.
Yeah, not that I know of. Like it's just what they picked, I guess. Like not the best. No. The rest of them are like A, B, C, M, X. So I have no idea why they skipped a bunch of letters and went right to M and X.
Are solar flares considered part of the sun? This is kind of an interesting question, because we are learning a bit more about the sort of like the composition, sort of like the different layers. So yeah, would you consider solar flares to be part of the sun?
No, I'd say like they originate from the sun, right? Because it's like what we consider a solar flare, and what I understand a solar flare to be is like the photons of like the light that we see released from the sun. not necessarily parts of the sun itself. I would consider like a CME, like a coronal mass ejection, like part of the sun, because that's like the plasma and stuff gets involved. Whereas a solar flare is just a bright flash of light.
Interesting. Yeah. And of course, with that new data, especially from the Parker Solar Probe, we're certainly, redefining kind of like what we think of as the sun, because it's much larger in scope than what we just see even through this telescope image, right? Yeah.
Like I think recently the Parker Solar Probe, I talked about a couple weeks back, but it like found the line where like the sun's atmosphere ends and this like stellar wind begins, right? Because stellar wind like comes from the sun, but we don't have a precise cutoff. Like we're trying to find that out, or we have, and whatever, it's up for debate. But yeah, the sun's a lot more complicated than we give it credit for, I think.
Awesome. Well, we got our last 10 minutes of the show, Marley. We've got actually another big story to get to. We could probably dedicate a whole episode to this, but there was a really important survey that just came out that is going to define a lot of the planetary science that's going to be coming over the next decade or two, and that is the Decadal Survey. And this is basically a bunch of scientists that come together to come up with strategies for what they believe the next missions should be. So what are some of the results of the most recent Decadal Survey?
So the whole survey, if we wanted to dedicate a whole episode to it, we could, because it's 780 pages long. I have not read the whole thing. I've read the Spark Notes. But yeah, so every 10 years, NASA asks scientists, like, what should we do in terms of planetary science? There was another one done for like stellar astrophysics and stuff a couple months ago. And what should be top priority? And so just to give you an idea of how large it is, they started working on it in late 2019. There were half a dozen committees. They met over like at least 20 times to talk about it. And so the initial takeaways we get are the flagship missions. And so these are the largest missions that NASA wants to get, what should we dedicate all our resources to, the largest ones. So these are usually the most expensive. And so the current flagship missions are the Perseverance mission was NASA's flagship mission for last decade, and also Europa Clipper, which is set to launch in 2024. Right. And so they evaluated 6 potential flagship missions. And so some of the top priorities they came away with are the Mars Sample Return mission. And this is the highest scientific priority. So this is currently already in the works by NASA and the European Space Agency. And this involves, getting all those samples Perseverance is taking on Mars and getting them back to Earth, right, for study and analysis. So this is the highest scientific priority. The highest flagship mission priority is actually a mission to Uranus, which is, I wasn't surprised to hear about. I never really consider Uranus, so I guess egg on my face.
Yay for Uranus.
Yay, like finally getting attention, I guess. And so I was surprised about this because, we don't really talk about Uranus again, like only one, thing has flown past it and given images of it, like the Voyager, this is where the image on the right-hand side is from. But what's interesting about Uranus is that it is made up of a dense fluid of icy materials. So water, methane, ammonia, and it also has a small rocky core, but near the core, it's about 4,890 degrees Celsius. So near its core is very, very hot, but the rest of the planet is quite cold. It has methane, that's what makes it the blue-green color. And the minimum temperature of the atmosphere of the planet is negative 224 degrees Celsius, with winds that reach 900 kilometers an hour. And it's, it's also the planet that looks like when it rotates, it looks like a rolling ball, right? It rotates on its side. And so there's lots of interesting things about Uranus. But again, because it's so hard to get there haven't been a ton of missions dedicated to it. But we don't know a lot about it. And it's probably time we should learn more. And so that's probably why the flagship mission is most likely going to be Uranus, to dedicate a lot of time, money, and science to this planet, just to get an idea of what's going on over there.
Well, I wonder if we could go back to my grade 3 project. I picked Uranus as the planet to study, mainly because my last name shared the first letter with Uranus. And also, I just really liked the color of it as well. And it was kind of weird. I was drawn to Uranus at that time. But even back then, the knowledge we had about it is probably not that different than what we have today because we haven't really studied it that much.
We haven't really studied it that much at all. And like, again, well, because it's so far from the sun, studies will have to be, decades long to see, lots of change, kind of like how the Neptune study was like, almost 2 decades long to gather any information about it. So it's one of those, it's such a struggle to study things when you get that far because it's just very hard to get any information.
Yeah, and just looking at the ring set there, we actually have a question about the rings. Are they similar to the other rings in the other systems, or is that also a bit of a mystery? Like what's going on with the rings around Uranus?
We know that there's like 13 very faint ones, but I don't know enough about them. They're not as, magnificent as Saturn's rings, and they're about, I don't think they're as magnificent barely as Jupiter. So they're more in line with like Jupiter's very faint ring system, but we don't fully understand where or how Uranus got its rings either, I don't think.
And what about this season's? Got a question from Keith. Just given that it's tilted so extreme, what are the seasons like on Uranus?
I'm not great. Like is my first like initial thought. Yeah, because of its tilt, it probably has it's how do I explain this? It's always cold, but its orbit is also relatively circular. So the seasons aren't as insane, I guess, like as a planet with like much more elliptical seasons. And its tilt being so severe, it's like the sun shines directly over each pole. Like they're kind of the same, just tilted. I don't know how to explain it in a way that
So
helps.
Would it be sort of like the north and the south poles would get more of the temperature and the heat as opposed to places along the equator?
Yeah. So it's gonna be oriented different. Yeah. So the poles, because the north and where's my little laser pointer thing? The north and south poles are like here and here. So they get the brunt of the seasonal changes as opposed to the equator, where on Earth it's the other way around.
Right. Interesting. So the Santa Claus on Uranus is basically he's got a jacket on, but it's cold, but he's still got some sunglasses on because it's nice and sunny. Is that what you're saying?
I guess so. though the planet is still super cold. Like the average temperature is still like negative 224 Celsius. So it's just cold. It's a cold, frigid planet.
And actually, here's another really interesting question that I never really thought of. So because it's tilted on its side like that, the rings are more vertical, but why is that? Like, why is like the ring set still sort of like centered around that equatorial belt?
That's okay. So it's gonna have to go do a lot with the gravity of the planet and the motions, like the physics behind how the planet formed and how everything is spinning, and the previous motions they had before becoming the ring. So the gravity is actually kind of stronger along the equator because there's more material there, and so it's slightly stronger. So that's where everything's going to pull towards. And so because Uranus is rolling, spinning like this, it's not unreasonable to think that any of the material that went to form its rings was also moving in that direction, and so they all ended up moving like that.
Right. So that probably does, give more clues to Uranus being like all the other planets, but something colliding with it to put it in its current form. So it didn't start off like that. It was like the other planets and then was tilted by force of something else hitting it.
Yeah, like something knocked it on its side is like a current line of thinking. And so possibly whatever knocked it left debris behind, or stuff from Uranus came up when it was still like a young planet. And maybe that more of a rocky core is what helped form its rings. And now it's just rolling.
Awesome.
With the rings as well.
Well, Marley, we've reached the rest of our episode. There were so many great questions.
No, there was
we even
still
have one more
story. Yeah,
I know. Let's quickly tease. We'll talk about it more.
It is a tease because they're also teasing it because the other flagship is Enceladus orbiter lander bracket if funding allows. So we'll see. We'll see.
Well, we are going the Orbit Clipper is going to Europa, so that is going to be perhaps a little bit of a preview as well to Enceladus. It'll be a similar type of mission, still trying to look for those signs of life inside the water of both of those icy moons. So very exciting stuff. Thank you so much, Marley, and thank you all, folks, for joining us here for another episode of Ask an Astronomer. We'll be here in 2 weeks, same time, which will be on May the 5th. That is Revenge of the 5th. We actually have a really fun event coming up on both May the 4th, and online-only events where we're going to be talking about this book that I have in my hands right here. It's called Star Wars Multiverse, if you can see it there, by Carmelo Estrich. And we're going to be talking about a whole bunch of really cool cultural aspects of the Star Wars universe, and the whole universe, not just the movies, but the books, the TV shows. I actually just finished Rebels, and I cried during the last episode. So
Heartbreaking.
it's a large universe and lots of really interesting cultural aspects to talk about in the Star Wars universe. So that's going to be on May the 4th. You can check that out on our website. And then we're going to have an in-person event on May the 5th, where we have members of the 501 Legion. And so these are the cosplayers that come up as in their costumes, Mandalorians, Darth Vader, the Imperials. They're going to be here in person. So you're going to want to get a ticket for that on May the 5th. And Marley's going to do a really cool presentation in the planetarium on that night. And of course, we've got an event tonight as well. So much going on that's going to be in person, and we're also going to be streaming what's happening in our planetarium, talking about Venus, another kind of forgotten planet, but forgotten no more. There is 3 new missions going to Venus, and we've got Megan Russell from the Planetary Institute that has come up from Colorado, is going to be here in person joining Marley for a really fun presentation about Venus. So you can come by and check that out in person, or you can also join online. Go to spacecenter.ca events for all of that information. And of course, we will see you right here in 2 weeks. Until then, take care.